Welcome to the deep dive. Today, we're going microscopic
Oh, yeah.
to explore the building blocks of, well, everything.
Everything.
Matter.
That's right.
Our goal today is to help you understand atoms,
Okay.
elements,
Yes.
molecules, compounds, and mixtures, and how they relate to each other.
Lots to unpack.
Yeah, we've got a really insightful educational presentation to guide us on this deep dive.
Sounds good.
So get ready
Yeah.
to unlock the secrets of matter.
I'm excited.
Me too. It's amazing how these fundamental concepts really underpin our entire world.
Right.
And we rarely ever stop to think about them.
Yeah, it's true.
Did you know that even something as simple as a glass of water is actually an intricate dance of elements and bonds?
Absolutely. It's incredible.
So where do we even begin with something like this?
Well, I think the best place to start is with the concept of atoms.
Okay.
These incredibly tiny particles
Yeah.
that make up all matter.
Oh, everything.
Everything. Yeah.
Wow, and how tiny are we talking?
So tiny that it's almost impossible to imagine.
Okay.
But to give you a sense of scale,
Yeah.
imagine this.
Okay.
If an apple were the size of the Earth,
Okay.
an atom would be about the size of a regular apple.
Wow, that's mind-boggling.
It really is, yeah.
So are all atoms the same?
That's where elements come in.
Okay.
Elements are like the fundamental ingredients of the universe.
Well,
They
yeah.
can't be broken down into anything simpler.
In the purest form.
The purest form, exactly.
Okay. Okay.
Each element has its own unique type of atom. For example, gold.
Uh-huh.
Gold is an element, and it's made up of gold atoms.
Okay.
That's what gives it its unique properties.
So the gold atoms are what give gold its properties.
Exactly.
Got it.
And get this, there are over 100 different elements,
Wow.
each with its own set of properties.
That's a lot.
Like oxygen,
Yeah.
essential for us to breathe, and hydrogen,
Yeah.
the lightest and most abundant element in the universe.
It's incredible to think that everything we see and touch is made up of these tiny building blocks.
I know, right?
Now, I remember learning about a scientist named John Dalton and his atomic theory.
Yeah, John Dalton.
What exactly did he contribute to our understanding of matter?
Well, he was an English chemist and physicist,
Okay.
lived in the late 18th and early 19th centuries.
Okay.
His atomic theory
Yeah.
was revolutionary because it proposed that all matter is made up of these tiny, indivisible particles called atoms.
Okay, so even if you were to smash something into a million pieces,
Right.
the atoms would still be intact.
Exactly. You're just breaking it down into smaller pieces,
Sure.
but the atoms themselves remain.
The fundamental building block.
Yes.
Okay.
Dalton also realized that elements are characterized by the weight of their atoms, and that different elements have different types of atoms.
So he essentially laid the groundwork for the periodic table,
You got it.
which organizes all the elements based on their properties.
Exactly.
Now, I know that atoms themselves aren't the smallest things in the universe.
That's right.
They're actually made up of even tinier particles.
Even tinier, yeah.
Right.
Yes.
Can you talk a little bit about that?
So we need to dive even deeper into the structure of an atom
Okay.
and explore the world of protons, neutrons, and electrons.
Oh.
These subatomic particles are what give atoms their unique characteristics.
Okay, I vaguely remember these from school,
Yeah.
but can you give me a refresher?
Sure.
Like what they are and where they hang out inside an atom?
Protons and neutrons,
Okay.
they're found in the nucleus,
Okay,
which is the central core of the atom.
got it.
Protons carry a positive electrical charge,
Okay,
while neutrons have no charge.
so the nucleus is kind of like the positively charged heart of the atom?
Yeah, a good way to think about it.
Okay.
And then we have electrons,
Okay.
which carry a negative charge
Okay.
and are found outside the nucleus in regions called electron shells.
Okay.
They're constantly moving around the nucleus.
So kind of like planets orbiting a star.
Exactly. Good analogy.
Okay, so we've got these tiny particles
Right.
with different charges,
Yeah,
and the interactions between these charges are what give atoms their properties.
exactly. And those interactions determine how atoms bond with each other to form molecules.
Okay, let's talk about molecules.
All right.
Now, this is a term we hear all the time.
Yes.
But what exactly is a molecule?
So a molecule is formed when two or more atoms bond together.
Okay.
Think of it like atoms linking arms to form a more complex structure.
Okay.
Now, it doesn't have to be different types of atoms.
Okay.
It can be the same.
Okay.
For instance, oxygen gas, O2,
Yeah.
which has two oxygen atoms bonded together.
Okay.
But it can also be different types of atoms,
Right.
like water, H2O,
Yeah.
which has two hydrogen atoms bonded to one oxygen atom.
Ah, that's why we see the little subscript numbers in those chemical formulas.
Oh,
Like
yeah.
H2O, it tells us how many of each atom are in the molecule.
Exactly. It's a shorthand way of representing the composition of a molecule.
Got it.
Yeah.
This is all starting to click into place.
Okay.
But now I'm curious about compounds.
Right.
How are compounds different from molecules?
A compound is a specific type of molecule.
Okay.
It's formed when two or more different elements combine chemically in a fixed ratio.
So all compounds are molecules.
Yes.
But not all molecules are compounds.
That's right.
Kind of like how a square is a rectangle, but not all rectangles are squares.
A perfect analogy.
Okay.
For example, water, H2O, is a compound because it always has two hydrogen atoms bonded to one oxygen atom.
Okay.
Table salt, NaCl, is another example,
Yeah.
formed from the elements sodium and chlorine.
So the elements in a compound always have to combine in a very specific ratio.
Precisely.
Is that why water is always H2O?
Yes,
And not, say, H3O?
exactly. And this fixed ratio gives compounds their unique and predictable properties.
So water has a very different boiling point than either hydrogen or oxygen on their own?
That's right. Fascinating.
It is.
So the way elements combine really dictates the characteristics of the compound they form.
Exactly.
Okay, so let's shift gears and talk about mixtures.
Okay, mixtures.
This is where things might get a bit, well, mixed up.
Yeah, a little more complicated.
So how are mixtures formed?
Mixtures are formed when two or more substances combine
Okay.
physically,
Okay.
but not chemically.
Oh,
Unlike compounds, the substances in a mixture retain their individual properties.
so it's like blending ingredients for a smoothie.
Right.
You're combining different fruits and veggies,
Yeah,
but they don't chemically change into something entirely new.
that's a great analogy. You're not changing the chemical makeup.
Right.
You're just mixing them together.
And because the substances in a mixture aren't chemically bonded,
Yes,
they can be separated by physical means.
that's right.
So I could theoretically separate the ingredients in my smoothie back out.
In theory, yes, it might be a messy process.
Okay. Probably wouldn't taste very good.
Yeah, probably not. But you could do it.
Yeah.
I'm starting to see the key difference between mixtures and compounds.
Good.
Now, I know there are different types of mixtures, right?
Yes.
Something about homogeneous and heterogeneous mixtures.
You're right.
Can you break those down for me?
There are two main types of mixtures, and they're distinguished by how evenly the substances are mixed.
Okay.
A homogeneous mixture,
Okay.
also called a solution,
Okay.
has a uniform composition throughout.
Okay.
You can't see the individual components.
So like salt water?
Exactly. You can't see the individual salt crystals once they've dissolved.
Because they're evenly distributed at a molecular level.
That's right.
Okay, and air is another example
Air's another great example.
of a homogeneous mixture.
Yes, it's a blend of gases like nitrogen and oxygen, but they're so evenly mixed that you can't distinguish them.
Visually.
Visually, you can't tell.
Okay, what about heterogeneous mixtures?
Heterogeneous mixtures have a non-uniform composition,
Okay.
so the components aren't evenly distributed. You can often see the separate parts.
Like a salad
Exactly, like a salad.
with lettuce, tomatoes, and cucumbers.
Yeah, you can clearly see all the different ingredients.
So in a heterogeneous mixture, the different substances maintain their distinct identities.
That's right.
Got it.
Now we've covered a lot of ground, but there's still so much more to explore in the world of mixtures.
Like what?
Well, there are special cases like colloids, which have properties that fall somewhere between solutions and suspensions.
Colloids. I'm intrigued.
They're very interesting.
Okay, but before we dive into those, let's take a quick pause.
Sounds good.
Let our listeners digest all this amazing information.
A lot to take in.
We'll be right back to unpack even more about the building blocks of matter.
Looking forward to it.
Me too.
All right.
Welcome back to the deep dive. Before the break, we were starting to unravel the mysteries of mixtures.
Lots of mysteries in mixtures.
You mentioned something called colloids.
Oh yeah, colloids.
What makes them so special?
Colloids are fascinating because they blur the lines between homogeneous and heterogeneous mixtures.
Okay.
They appear uniform at first glance like milk or fog, but they actually contain tiny particles that are larger than those found in solutions.
So they're kind of in between a solution and a suspension.
Exactly.
Okay, can you break that down for me?
So in a solution,
Yeah.
the particles are completely dissolved and invisible.
Like salt and water.
Like salt and water, exactly.
Okay.
In a suspension, the particles are large and settle out over time,
Okay.
like sand in water.
Got it.
Colloids have particles that are somewhere in between.
Okay.
They're small enough to stay suspended,
Okay.
but large enough to scatter light.
Ah, now you're talking about the Tyndall effect.
Yes, the Tyndall effect.
I remember seeing this demonstrated in science class,
Right.
shining a light through a mixture to reveal those tiny particles.
Exactly.
That was always fun.
It's a cool effect.
Yeah.
and a great way to distinguish between a true solution and a colloid. When you shine a beam of light through a colloid, like milk, the light scatters and becomes visible.
So it creates a sort of beam through the mixture?
Exactly.
Kind of like shining a flashlight through fog.
Yes, exactly like that.
But you can see the beam because the light is scattering off the tiny water droplets.
That's right.
So cool.
The Tyndall effect is basically just light scattering.
Okay.
But it tells us something important.
About the size of the particles.
Yes, about the size of the particles in a mixture.
Got it. And it's not just a cool visual effect.
Right.
The Tyndall effect has real-world applications.
It does, for instance.
Yeah.
It's used in nephelometers.
Nephelometers.
Which are instruments that measure the concentration of particles in a liquid or gas.
Okay, so the next time I see a beam of sunlight illuminating dust particles in the air, I'll know that's the Tyndall effect in action.
Exactly, you got it.
Very cool.
Now, before we move on, I want to circle back to solutions for a moment.
Okay.
Because they play such a crucial role in chemistry and everyday life.
Yeah, for sure.
We often think of solutions as liquids, but they can actually exist in any state of matter.
Really?
Solid, liquid, or gas.
So air is a solution even though it's a gas?
That's right.
Wow.
Air is a solution of gases, primarily nitrogen and oxygen.
Okay.
And solid solutions exist too, like brass, which is a solution of copper and zinc.
Okay, so the key defining feature of a solution
Yeah.
is that the substances are evenly mixed.
At a molecular level.
At a molecular level, regardless of their state of matter.
Exactly.
Got it.
Now, let's focus on a specific type of solution that's essential for life as we know it.
Okay.
Aqueous solutions.
Okay, I know aqueous has something to do with water.
It does.
But can you explain exactly what makes a solution aqueous?
An aqueous solution is simply a solution where the solvent, the substance that does the dissolving, is water.
Okay.
Think of it like this.
Yeah.
Water is the host of the party,
Okay.
and the dissolved substances are the guests.
So in salt water, water is the host and salt's the guest.
Precisely.
Okay, got it.
And in a chemical equation, we indicate that a substance is dissolved in water by adding AQ after its chemical formula.
Okay.
For example, NaClQ represents salt water,
Mm-hmm.
with the AQ signifying that the salt is dissolved in water.
Okay, that makes sense.
Good.
Why is water such a good solvent? What makes it so effective at dissolving other substances?
Water is a remarkable molecule
Yeah.
with some unique properties
Okay.
that make it an excellent solvent.
Like what?
Well, for one, it's a polar molecule,
Okay.
meaning it has a slightly positive end and a slightly negative end.
Okay, remind me what polar means again?
Think about a magnet
Okay.
with a north pole and a south pole.
Okay, yeah.
That's similar to how a polar molecule works.
Okay.
Water has a slightly negative charge on the oxygen atom
Mm-hmm.
and a slightly positive charge on the hydrogen atoms.
Okay.
This polarity allows water molecules to attract and surround other charged particles, effectively pulling them apart and dissolving them.
So water molecules act like tiny magnets, attracting and surrounding the particles of other substances.
Exactly.
That's why water can dissolve so many different things,
Yes.
from salt and sugar to gases like carbon dioxide.
That's right.
Wow, I never realized how crucial water's polarity is for its ability to dissolve substances.
That's very important.
So are all the things that dissolve in water also polar?
That's a great question.
Yeah.
The general rule is like dissolves.
Yeah.
So polar solvents, like water,
Uh-huh.
are good at dissolving polar substances and ionic compounds, which have positive and negative ions.
Okay.
Non-polar solvents, like oil,
Yeah.
are better at dissolving non-polar substances.
Ah, that's why oil and water don't mix.
Exactly.
They're like two different dance floors, each attracting their own kind of dancers.
A perfect analogy.
I like that one.
Good.
Now, let's talk about some of the incredible things that happen when substances dissolve in water.
Okay.
The properties of a solution can be quite different from the properties of its individual components.
That's right.
Like salt water has a higher boiling point than pure water, right?
Exactly.
Right.
That's just one example.
Yeah.
Aqueous solutions are involved in countless chemical reactions that are essential for life.
Wow.
They transport nutrients in our bodies,
Uh-huh.
regulate our temperature,
Okay.
and play a vital role in everything from cooking to cleaning.
It's amazing to think that something as simple as water dissolving a substance can have such profound effects.
I know, it really is remarkable.
You mentioned in my notes that I'm interested in cooking.
I did.
Well, understanding the chemistry of aqueous solutions
Yes.
can take your culinary skills to a whole new level.
Absolutely. It can really change the way you think about cooking.
I'm already thinking about how these principles apply to everything from making a perfect cup of tea to baking a delicious cake.
For example, when you make tea, you're essentially creating an aqueous solution.
Okay.
By dissolving the tea leaves in hot water,
Right.
the temperature of the water affects how quickly the compounds in the tea leaves dissolve and how strong the flavor becomes.
And I'm guessing the ratios of ingredients in a cake batter are
Yeah.
crucial for creating the right texture and consistency.
Absolutely. Baking is all about chemical reactions, and many of those reactions involve aqueous solutions.
Give me an example.
When you mix baking soda with an acidic ingredient like buttermilk,
Okay.
you create carbon dioxide bubbles
Yeah.
that make the cake rise.
So cooking is essentially a delicious form of chemistry.
It really is.
I love that.
And understanding the science behind it can help you become a more creative and confident cook.
I agree.
But let's not get too sidetracked by our culinary adventures.
Right, back to the science.
We still have more to explore in the world of matter.
Okay.
We've discussed pure substances and mixtures, but there's another crucial distinction that's important to understand.
Okay, what's that?
The difference between physical and chemical changes.
Welcome back to the deep dive. I'm still reeling from that culinary chemistry revelation.
It's pretty amazing, isn't it?
I'll never look at my kitchen the same way again.
I know, right?
Yeah.
It's like a whole new world opens up when you start to see the science behind everyday things.
Absolutely. But before I rush off to experiment with my baking soda and buttermilk, let's get back to our exploration of matter.
Okay, sounds good.
You mentioned we need to understand the difference between physical and chemical changes.
Yes, that's an important distinction.
Can you explain what that means?
Of course. So everything in the universe is constantly undergoing change,
Okay.
but not all changes are created equal.
Right.
A physical change alters the form or appearance of a substance,
Okay.
but it doesn't change its chemical composition.
So it's like changing the outfit of a dancer.
Exactly.
The dancer's still the same, just wearing different clothes.
Perfect analogy.
Okay.
Think about ice melting into water.
Okay.
It's a physical change because the H2O molecules are still the same, just arranged differently.
Got it.
Cutting a piece of paper is another example.
Okay.
You're changing its shape,
Yeah.
but not its chemical makeup.
So if I crush a can, it's still aluminum,
Exactly.
just in a different form.
Yes, the atoms are still the same.
Got it.
Now, a chemical change is a bit more dramatic.
Okay.
It involves a rearrangement of atoms,
Okay.
resulting in the formation of new substances with different properties.
So it's like a caterpillar transforming into a butterfly.
A complete change in identity.
Exact.
Burning wood is a classic example of a chemical change.
Okay.
The wood reacts with oxygen in the air, producing ash, carbon dioxide, and water vapor.
Completely new substance.
Entirely new substances with different properties.
So the chemical bonds between atoms are broken and reformed,
That's right.
creating something new.
Exactly.
Cooking is full of chemical changes, right?
Oh, absolutely.
The browning of meat,
Yes.
the baking of bread,
Ah.
the caramelization of sugar.
All involve chemical reactions that transform the ingredients.
Okay, so we've got physical changes, which are like rearranging furniture.
Okay.
And chemical changes, which are like building a whole new house.
I like that.
How can we tell if a change is physical or chemical?
That's a good question.
Are there any clues to look for?
There's some telltale signs.
Okay.
A changing color,
Uh,
the formation of a gas, like bubbles,
okay.
the release or absorption of heat,
Got it.
or the formation of a precipitate, which is a solid that forms from a solution.
So if I see something changing color, bubbling, getting hot, or forming a solid, it's a good bet that a chemical reaction is taking place.
Exactly. Those are all good indicators.
This has been an incredibly eye-opening journey into the world of matter.
I agree.
We've explored the tiny building blocks that make up everything around us, from atoms and elements to molecules and mixtures.
And everything in between.
We've learned how chemical bonds hold atoms together, how the properties of substances can change, and how to distinguish between physical and chemical transformations.
It's amazing how much we've covered.
I feel like I'm seeing the world with a whole new perspective.
That's the power of understanding science.
Absolutely. And to our listeners, we encourage you to keep exploring, keep questioning, and keep marveling at the incredible world of matter.
It's a fascinating world out there.
Who knew that something as seemingly simple as a glass of water or a slice of bread could hold so many secrets?
There's always more to learn.
Thank you for joining us on this deep dive into the building blocks of matter.
It was my pleasure.
Until next time, happy exploring.
Goodbye.